back, students. This is Dr. OJ tutorial. In this video, we shall discuss implicit differentiation with examples. Now, when we say implicit differentiation, all the previous examples we've discussed are explicit. Why? Because y is a dependent variable for x that happens to be independent. You know, all those ones have been y equals to something, y equals to something. But in this case, y is not defined explicitly. It is defined implicitly. You can see that we don't have y equals to anything here. So that is a kind of what we call implicit differentiation. Now, to differentiate anything like this, listen. Anytime you differentiate y under implicit differentiation, you always write the y dx. Again, anytime you differentiate y, you must always include the y dx. Okay, now let's go ahead. Now we have x squared y plus y squared x plus 4x is equals to 1. Take notes. X squared y is a composition function, or let me put it this way. It's a product function. It contains algebraic square of x, and it has a single a linear form of y. So you are multiplying x squared by y here. So you're going to use product rule here because you're having two different variables. Here also we have two different variables. Here we have, in fact, you can call this one single because this is a constant, so it will be easy. So in this case, now what I'm saying is that when you are differentiating product function, you apply product rule. Okay, let's go ahead. Now, and to make it easy for you, you might split it. Okay, let me show you. Let's pick this. X squared d of dx of y. Yes, that is, I bring x squared as a constant, I differentiate y. Then plus, I now bring y as a constant, and I differentiate x squared. That's the best approach. Okay, you can see that it will be easier for me to carry out the further evaluation of my differentiation. Now the next one, plus, let me bring y squared out, so I will differentiate d of x, then I will bring x out, I will differentiate y squared. Okay, then plus this one I don't need to split it. 4x is like a single variable, so I don't need to. D over dx of 1. Beautiful. Now let's go ahead. Now x squared. Now multiply by d. Automatically is dy dx. D of y dx, dy dx plus y. Then you now differentiate x squared. When you differentiate x squared, 2 times 1 here, you have 2x. Then you subtract 1 from 2, it's 1. So you can see what I did there. Y is a constant, that's what it's written out. Then 2 times 1, 2. Then x subtract 1. Then plus y squared out. Then differentiate x is 1. Yes, when differentiate x is 1. Okay, let's see. Y equals to x. 1 here times 1 here, that's 1. Then x raised to power 1 minus 1, 0. So that is what 1 times s raised to power 0 is 1. So it's 1. Okay. Now, we have done that. Plus x is a constant now. Now, this one, you want to differentiate y squared. So that would be what? 2y. Then dy dx. I told you, anytime you differentiate y, you must write the y dx. You'll be wondering, sir, but here we differentiate, yes, when differentiate y is 1. So you have to write dy dx. Is 1 times dy dx, still dy dx. So we actually don't have no problem here because it's just y raised to power 1. So just write dy dx straight off. But this is y squared. So you first of all differentiate that y. 2 times 1 here is 2. Then y raised to power 2 minus 1. That's y raised to power 1. 1. As you can see, 2y. You now repeat, you now write dy dx. That's the rule. Then plus 4x, that is 4. You're asking why. Okay. 1 times 4, 4. X, as usual. Then 1 minus 1, 0. There's a constant 1 on top. Yes, x raised to power 1 is the same as x. So 1 times 4 is 4. Then x, 1 minus, you must always deduct 1 from the exponent when you are carrying out your differentiation, and that will be 0. And anything raised by 0 is 1, so 4 times 1 is 4. That's the reason. Okay, is equal to, this is a constant, 0. It's as simple as that. Yes, it's as simple as that. Now let's finalize it. Let's finalize it. To finalize this now, we expand x squared dy dx plus 2xy, yes, because 2x times y is 2xy, plus y squared plus 2xy as well, dy dx, that is this, then okay, plus 4 equals to 0. Okay, now let's collect like terms and see what happens. Let's collect like terms and see what happens. Okay, collect like terms. Collecting like terms gives the one that has dy dx, x squared dy dx plus 2xy dy dx plus 2xy plus y squared. You can take this 4 here and become 0 minus 4 because it's constant. Yes. So we cannot have the one that has the as, so we factor out the y dx, we factor it out. Yes, the y dx into, we factor it out, it's common. So we'll be having x squared left here plus 2xy, no more dy dx, fine. Then plus 2xy plus y squared equals to minus 4. Okay? So now that we have factored out the y dx, it will be proper for us to take all these ones to the other side as well. Yes, because our target is to get the value of the y dx. So the y dx into x squared plus 2xy is equal to minus 4 minus 2xy minus y squared. Yes. Why? Because we want to factor out those that have the y dx on the left and those that don't have the y dx on the right, so that we're able to get the y dx. So with this now say divide both sides by x squared plus 2xy. Yes, by the time you divide both sides, because we want to make the y dx the subject of formula. So now divide by what is beside the y dx. So that will now give us, therefore the y dx will be minus 4 minus 2xy minus y squared all over x squared plus 2xy. So that solves the problem. So that is how to solve problems of implicit differentiation. So let's look at another interesting example still under implicit differentiation. Let's try this. Let's try this. Differentiate example 2. Example 2. Find the y dx given the equation. What's the equation? X squared y plus xy cubed plus 3x is equals to 0. This is even easier. All right, it's even easier. Let's do that. Oh yeah. Don't forget d. Just say x squared d of dx of y. As this, I'll put x squared as my constant. Then y is a constant now. D of dx of x squared. Okay, I interchange them. Then plus x d of dx of y cubed, then plus I bring y cubed out, d over dx of x, then plus d of dx of 3x is equals to d of dx of 0. Okay? Yes. So what follows? You have x squared y, and you know y, when you differentiate y, dy dx now. I hope you understand. X squared dy dx. If you differentiate y alone, you are going to get 1. Then 1 times dy dx. I told you anytime y is being differentiated, you must multiply the result by dy dx. So that's why if you differentiate y, is going to be 1. So 1 times dy dx is dy dx. So instead of stressing yourself, just write dy dx here. Okay. Then plus y. If you differentiate x squared, that is what? 2x. Then plus x. Now differentiating y cubed, that's 3y squared dy dx. Let me explain this again. 3 times 1 here is 3. Then subtract 1 from 3, you have y squared. So because we have differentiated a dy dx factor, we have to multiply the value we obtain by dy dx. So that's why we are writing dy dx here. Then plus y cubed. When differentiate x is 1. So times 1 is 1. Okay. So you don't need to repeat 1 there. Plus this is 3. Then equals to 0. Okay. Let's expand. X squared dy dx plus 2xy plus 3xy squared dy dx plus y cubed plus 3 equals to 0. Okay. Now, what next we do? We collect like terms. Okay. So without wasting our time, we collect like terms. All right. X squared dy dx plus 3xy squared dy dx. No other values of dy dx. So we are through with the one that has dy dx. Then plus 2xy plus y cubed plus 3 equals to 0. So dy dx is common. So dy dx, we factor it out. We have what left here? X squared plus 3xy squared. No more dy dx. So it will be better we take the other ones to the other side without wasting our time. Minus 2xy minus y cubed minus 3. Yes. Okay. Now the last thing we take now is divide both sides by the factor behind the dy dx. Now say, therefore, dy dx now will be minus 2xy minus y cubed minus 3 all over what? X squared plus 3xy squared. So that solves the problem. So with this, we have come to the end of differentiation of implicit function. Do well to click on the notification bell so that each time I upload new video, you'll be daily informed. Take care.